Hey guys, welcome to today's lesson. I'm Mr. Adamson here, and we're going to talk about chemical change. So the process that involves recombining atoms and energy flows. So an important example of chemical change. So chemical changes occur when a substance or substances react in a chemical reaction to create a different substance or substances. And I'll say that a whole bunch of times fast, but anyways, you have a couple things coming together to form something different. Now, the substances that react are called the reactants, and their reaction produces new substances, which are called the products. And now, products and reactants also have different properties, which is key to note. And the flow of energy into or out of systems drives chemical change. So there's an important part right there. The flow of energy into or out of systems drive chemical change. Now, chemical reactions are used in a wide variety of applications. So they can be fast or they can be slow. So an example, you have a battery releasing energy to power a flashlight. And the reverse of that is a chemical reaction that recharges the battery when it is run down. So you have the fast type, so the battery providing power to the flashlight, so you have light, so that's a fast, and then recharging, which is kind of slow. Now, chemical reactions also occur naturally in countless biochemical processes, and the most easy example that we see of that and know of is photosynthesis. Photosynthesis, so what plants do to produce energy for themselves, and cellular respiration, what living organisms do, so such as human beings, what we do to produce energy for our body and produce ATP, and that's another concept we'll get into a little bit later, and you'll get more into biology. Now, reactions that form gases. So these can be sudden and dramatic, as in an explosion, or slow and steady, as in a rising cake. Now, an explosion occurs when a small amount of solid or liquid converts quickly to a large volume of gas. And other than an actual explosion or something blowing up, a really good example of this is the inflating of an airbag in a car when an accident happens. So you have a couple compounds that are coming together to produce a large amount of gas that blows out into the airbag. And I mean, that's happening very quickly, so your face doesn't slam off the dashboard or the steering wheel. So I mean, you know how fast that is occurring if you've ever been in an accident. Now, reactions that form solids. So here, an example of this is 5-minute epoxy glue. So any of you guys who have used this at home or kind of liquid cement, so when combining the two chemicals in the glue, so they form one large molecule. And this is usually a solid hard substance from this is formed. And there's a few other examples that you might have out there. Now, chemical states. So states in a reaction are provided to give as much information as possible about the reaction. And we talked about the states earlier when we talked about identifying ionic and molecular compounds and acids, where, acids for the most part are in aqueous solutions, ionics or compounds are solid, whereas a molecular compound we can be looking at for the most part in liquid or gas and sometimes solid forms. Now, the guidelines for the states of substances at room temperature. So elements. So metals are solid for the most part, except mercury, which is a liquid. Sulfur, phosphorus, and carbon are solid for the most part. And most of the diatomic elements, though, are gases, except for bromine, Br2. So remember we talked about diatomic before, like N2 and O2. I mean, nitrogen and oxygen, these are gases. But bromine, Br2, is liquid, and iodine, I2, is solid. So what's left off that periodic table that we haven't really talked about? And that's where we talk about, again, which we mentioned up top, if you're thinking about the polyatomic, so the sulfur and phosphorus, so S8, and phosphorus, so P4. We talked about ozone, O3, well, that's in a gas form. So a few different examples out there. Now, compounds. So all ionic compounds are solid at room temperatures. An ionic compound that is very soluble is shown as aqueous when it is dissolved in water. Now, an ionic compound that is slightly soluble is usually shown as solid even when it is in water. Now, molecular compounds are very difficult to predict. The smaller the molecules are, the more they tend to be gases. And the larger they are, the more, that should be more, not or, they tend to be liquids than solids. So example, CH4, which is a gas, which is methane. C6H14 is a liquid, and C18H38 is a solid, which is beeswax. Now, energy changes. So energy flow is an essential part of any chemical reaction. And we have kind of two ways that energy can flow here. We can have energy being released, which is an exothermic reaction, and we can have energy being absorbed, which is an endothermic reaction. Now, exothermic reactions. So they release energy usually in the form of heat, light, or electricity. So example, the lead acid storage batteries. You can have combustion of fossil fuels, so coal, oil, and natural gas. And combustion is a chemical reaction that occurs when oxygen reacts rapidly with a substance to form a new substance and gives off energy. And this is called burning, and we'll do a few combustion reactions within class. Now, coal is used to produce electricity, and the heat released by coal combustion is used to make steam, which drives turbines to produce electricity. Carbon dioxide is also released, so you can see bringing together carbon and oxygen, we form carbon dioxide and energy. Now, endothermic reactions, these absorb energy, so example, a cold pack as a chemical reaction, or as the chemical reaction, they absorb energy and the whole mixture cools down. So there's an easy example of that. And now they may be our biochemical reactions that we talk about now, so things that are occurring naturally within systems on Earth here. These may be endothermic or exothermic. And they happen at an organism's internal temperature, and they are always helped by enzymes, so biological catalysts. So meaning enzymes usually help speed it up or keep it constant over a period of time. Now, catalysts are chemicals that speed up again, but are not used up. And that's the important part there. They're not used up within the reaction. So one of the most important chemical reactions on Earth is photosynthesis. Now, photosynthesis is an endothermic reaction, so energy appears on the left-hand side of the chemical reaction. So you see we have energy plus carbon dioxide plus water gives us C6H12O6, which is glucose, plus oxygen, and this energy being the light from the sun. Now, almost all food on Earth begins with this reaction in the leaves of plants. Oxygen is a byproduct of this reaction, and most oxygen comes from photosynthesis. And that's an important part there, that oxygen within photosynthesis being a byproduct is actually a waste product of the plant. The plant doesn't need the oxygen, therefore it expels it out, but is very important for the rest of life on Earth here. Now, cellular respiration is a reverse process of photosynthesis. Both plants and animals use cellular respiration to release energy that is used to drive all the chemical reactions in their tissues and organs. And cellular respiration is an exothermic reaction, meaning that you see energy on the right-hand side now as a product, not a reactant. So we have oxygen and glucose, okay, being formed as our reactants and forming the products of energy, carbon dioxide and water. Now, all reactions involve the production of new substances with their own characteristic properties. So, example, their state at room temperature, their melting point, their color, their density. Okay, they involve the flow of energy, and when new substances form in chemical reactions, sometimes chemical changes of state can be observed. And all chemical reactions are consistent with the law of conservation of mass. Now, the law of conservation of mass was developed by Antonio Lavoisier, and Lavoisier concluded through his experiments that the total mass of the reaction system never changes. So the reaction system includes both the reactions and the products. I mean, the reactants equal the products. And note, not all reactions can be seen. So example, oxygen. So things that are occurring with oxygen, we can't always see that. So combustion reactions, when it's first occurring, we can't maybe see until you have that reaction starting to ignite. So if you flip to page 84 within your textbook and you read paragraphs 2 and 3, it talks a little more about the conservation of mass with Lavoisier and what he was doing. Now, what he developed from his studies was, again, the law of conservation of mass, and so that being the total number of atoms present before a reaction is equal to the total number of atoms present after a reaction. And that's the kind of little bit on chemical reactions and energy flow and endothermic and exothermic reactions. So hopefully you can take a little bit about that today, and we'll further on discuss these ideas within class.